And we are back. Okay, so a quick little example problem here. We're going to look at how many nuclei of uranium-238 remain in a rock if the activity registers 640 decays per second. And if you didn't know this off the top of your head, the half-life of uranium-238 is 4.468 times 10 to the ninth years. So a very long time. So in order to solve this problem, what we need to recognize is that the equation we could use here is a delta N over delta T. This is the activity, and that's going to be equal to technically a negative, but lambda N naught here. Okay, we're just kind of ignoring the negative at the moment. But what we can pretty much say here is if we're looking for how many remain at this point in time, we can say that our activity is measuring 640. So this activity here is 640, and that will equal lambda times N naught, where we're probably going to find a fraction of that. In order to find this lambda, we actually need to use our half-life. Lambda is equal to the natural log of 2 over tau. So if we do this for the natural log of 2 over tau, for our half-life here, what we will find is that our value that we've got is, so natural log of 2 is 0.693. I know some of you just call that 0.7, rule of 7. And then we divide that by our tau, and we actually need to put this in terms of seconds here, which is a little weird. So we're going to get 4.468 times 10 to the ninth years. And then if you want to know how many seconds are in a year, it's about pi times 10 to the 7th. It's 3.16, so about pi, times 10 to the 7th seconds per year. So we're going to get a nice value of lambda out of this. So when we do that, what we're able to do is turn this value of lambda, and when we run that number for all of that, we get a value of lambda of very small, 4.9 times 10 to the minus 18. And then this will be n. It'll be how many nuclei remain here. So we just divide by the 4.9 times 10 to the minus 18, so we'll get a large number here. So we do 640 divided by that lambda value, and what we get here is a value of n equaling 1.3 times 10 to the 20th, and this is nuclei. So that's how many nuclei of this uranium-238 remain in our rock. Now, we actually use this idea of uranium with its very long half-life here for some dating of the Earth. It's actually one of the ways that we can figure out how old the Earth is. We also use carbon to do this, and one of the things you may have heard out in the past is radioactive carbon dating, because that gives us a nice time period of how long the Earth has been around and how long certain things have been around, like how old were the dinosaurs, right? So this is a quick little example on that, but this one is now finished. We've got a few more to go, but until next time, adios and take it easy.